Before we kind of get into today's material, so first of all, is there anyone in the room who has not been receiving emails from me? And you are, both of you? Are you enrolled?
Yeah.
As of when?
Last semester. Kind of.
And you haven't gotten an email from me?
No, I haven't.
Are you sure?
Pretty sure, yeah.
Are you sure? Because I generated the email list from Trailhead of all the enrolled students.
I'll check again today.
Send me your email, and then I'll add you to the list no matter what, and I'll send you all the. It's just been 236 emails that you missed, but I'll go ahead and forward all those to you today, and you can catch up on everything. Now I spent 2 emails, and I'll send them out to you.
I realized that in a while. Last time you tried to send out.
I haven't received your email. I don't do it. So technically you received it. Okay. All right. So just make sure that if you're not getting my email, that you send me the email. Also, if you read that email, and I've noticed over the last day or so that many of you have responded, I would like for each of you to send a picture with your name scrawled somewhere on the picture. Because what I'm going to do is make a little deck of cards with your pictures and names on them, from which I will randomly choose people throughout each lecture to answer questions. And the point of that is just to make sure you're awake and you're engaged. It's not the end of the world. If you can't answer the question, just don't be asleep. That's always a bad thing. And be here. Okay, if you're not here and I call your name, that's a bad thing for you. Generally speaking, I haven't really had to ding anybody for this. So don't be terrified of it, but it's just a way to kind of keep you on your toes during lecture. Also, a second thing, how many of you have a class immediately after this? And when I say immediately after this, you mean 12:15? 12:30. So this is every 12:15, and you have a class at 12:30.
It's also film studies, so.
Well, you're getting film like education in here. So.
See, I'll just turn that into our actual folder.
Okay, all right. Well, that. So, but 12:30 is the next class period, so I don't even think this room would be taken over before that. Okay, so that's just kind of checking in case I need to run over a minute or two or whatever. And I'm also thinking about. Well, no, I'm also thinking about sort of semi-unofficially or maybe officially having maybe like a 20-30 minute office hour in this room immediately after class. That way. Clarification of things, but I have to check whether this room is available. It might not be it. We'll see. So for those of you who just came in, you talked about the last part of the course. I missed it. So the people who just came in, have you gotten emails from me? You have. Okay, good. And make sure you send me those pictures if you haven't already, and we'll be good to go. So are there any questions about the structure of the course as it was laid out on the website? So we're going to have weekly homework assignments. My plan is to have them due on Tuesdays, so you'll have an assignment over a week's worth of material, and then on Tuesday you'll come in and you'll take a homework quiz at the beginning of that class. Sorry, I feel like an idiot standing at lectern. But it is very natural, I have to say. Have you been getting my emails?
Yeah.
Okay, good. Set it. So your homework quizzes will be on Tuesdays. I'm going to try, it looks like I'm going to have 2 hours of office hours Monday afternoon, probably from 2 to 4, and then 2 hours of office hours on Wednesday, and then I'll sprinkle the other hour somewhere in Thursday. But anyway, you will have some office hours on Monday prior to the homework quiz on Tuesday to get some help if you need it. I do have a TA for this course. I haven't met this person yet. I don't know what they do and don't know. They took this course at some point in the past. It's not Casey. It was going to be Casey, but they wouldn't give me Casey, and I'm mad about that. But anyway, I don't know how much this TA will be able to help you, how much he remembers from taking the course himself. We'll see how that goes. But anyway, just before spring break, probably just before spring break, we'll do a series of oral exams, and those are just going to be 15 minutes, you in my office, and I'll just ask you a couple of questions just to kind of gauge where you are in the course. And again, last semester I did this, or in the spring I did this with general relativity. It went pretty well. Anybody who didn't do well enough, I gave them a chance to repeat their oral exam, so it was fine. And then the only other exam on the course is a take-home final. Okay, so you won't have any in-class exams. But you will have these sort of in-class homework quizzes, and you can read about the structure of the homework quizzes on the course website. If you have any questions, just ask me about. Okay, so so every time I get to this course, or this or GR, either one, I have to recalibrate how I teach because I come out of teaching Physics 100 where students A, know nothing, B, don't care, and C, I use PowerPoints. And so this is all different because you know something, you care, presumably, and I've got to write on board. So a lot of times I have a lot more text than I should try and write on the board, so I have to get used to kind of reading. So technically the name of this course is Particle Physics, but you're very quickly going to find out that that's actually a really poor name for it. A better name, and by the way, all of my notes, including a lot of stuff that I won't be writing on the board, all that will be posted into the course website the afternoon after any given lecture, so you don't have to write everything down. A more appropriate title for this course, and it's kind of small font, Physics. So Particle Physics is the name of the course, but it should probably be called, do you know what it should be called?
Physics.
Joe! Well, that field would be a better word, but that actually happens to not be an answer. Physics at the fundamental frontiers with which we are currently confident. Because technically, if we go to the fundamental frontiers, we might be talking about something like string theory, but this is not a class in string theory. We're really going to be talking largely about something called the standard model, and the standard model is a description of what we've observed that we're very confident in. It's been verified to experimental tests time and time again. And moreover, it doesn't really utilize descriptions of things in terms of particles. Okay, rather, it uses these things called fields. So it's kind of weird to call it particle physics, but we do it anyway. Sort of a historical name for this. So before I get into even particle physics, there's a couple of pieces of nomenclature I want to get across because I'm going to use them. I don't want you to have a good idea of what I mean when I say these words. And now the three definitions I'm going to give you are somewhat unique to me. You're not going to find these universal in the literature. And in fact, we'll see contradictions to their use in this lecture today. But nonetheless, this is what I mean when I talk about these words. So first of all, we can talk about a system of mechanics. And when I refer to mechanics, I'm thinking of, can everybody see that? You guys in the back row, can you see that?
Yeah.
All right, good. When I refer to mechanics, I'm talking about a framework for describing the evolution of a system. Chalk. I haven't written with chalk in a long time. Okay? So now that might seem a little vacuous, but then we can take it and we can step it up a notch and we can then talk about a theory. And we get a theory if we take a framework applied to a particular context. Now I'm using words like context and system and framework to be intentionally vague because I want these definitions to apply to any situation or any kind of thing that we study in physics. But let me kind of specify the difference in one particular example, which at least half of this class will be very, very familiar with. If I were to ask you about special relativity, is special relativity a theory, or is it is it a mechanics, or is it a theory? What would you say?
Theory.
Awesome. So who says theory? Raise your hand. Who says mechanics? Okay, it's actually a framework of mechanics. And the reason I say that is because you can take any set of particles, you can take any interactions, and you can cast them in the framework of special relativity. Special relativity can be applied to many different examples. If, however, I take special relativity and I apply it to a specific interaction, for example, gravitation, then I'm working with a theory. Anybody give me an example of what that would be? General relativity, exactly. So for those of you who took GR, you might recall that that's a very significant difference between GR and special relativity. A lot of people think general relativity is just an extension of special relativity, but the relationship between them is quite different. General relativity is particularly focusing on a gravitational interaction, doing it relativistically. It's a nice book. Whereas special relativity is just a framework for describing many different contexts. Now that relationship gets a little more transmuted because you could also think of special relativity as a particular solution of general relativity. But in that context, you're not necessarily thinking of special relativity as a theory with its own solutions. General relativity is a theory. But anyway, so when I talk about mechanics, I'm going to be talking about things like special relativity. I'll be talking about things like Newtonian mechanics, quantum mechanics, those sorts of frameworks, versus theories where I'm looking at using those frameworks for specific contexts. And then last but not least is the idea of a model. And the idea of a model, which is of course going to be relevant for this course because we're going to be talking a lot about the standard model, is an effective theory that requires inputs that are chosen to match observation. Now this is, it's a little more wordy in what I have printed here, but I'm not going to write down all those words. But what I have in mind here is, it is a theory, so you're looking at a framework, so you're doing relativistic physics, quantum physics, or whatever. You're studying specific forces, okay? But it's called a model because some of the input that you need to work with that theory is not predicted by the theory itself. Okay? So for example, the electron mass. There's nothing in the standard model that predicts the value of the electron mass. The only thing you can do is go do experiments and measure it, and then use that value as an input into the standard model. Okay? It's effective. The word effective basically means that it doesn't have the complete information. So a theory in principle would have all the information. An effective theory is kind of acting like a theory, but you've got to grab some information that you can't really justify and just shove it in to make it work. Okay? So in contrast here, string theory, which we won't talk about a lot, but I'll mention from time to time, string theory is a theory. It has no inputs. Okay? The standard model is very much a model in the sense that it has these inputs that you just have to go and make experimental measurements and determine the values of them. Okay. All right. And again, not everybody agrees on this use of language, but the way that I use these words is following this scheme, so I just wanted to get that out there.
Foreman?
Yeah.
So ideally, we want to take the standard model and make it a theory so that we don't have any needs for inputs or just be itself.
Yeah. So there is ample evidence within the standard model itself, surprisingly, and this is something that we're going to spend a large portion of the last part of the semester studying. There's ample evidence within the standard model that it is not complete, that there is something more fundamental lurking out there. And the presumption on the part of all theorists is that that something, if it's the complete final fundamental something, would be a theory instead of some effective theory. But for the most part in this course, we're going to be studying things at the level of the standard model, so we will have to work with these inputs. But that's fine. Yes?
So there's like the mechanics on top of that input, or is that like the theory that doesn't need?
Well, mechanics this is a more general thing. I mean, you might be applying this framework to a particular example that might or might not require inputs. So for example, if you do non-relativistic electrodynamics, that's a model, right? Because you have to, if you're trying to describe electrons that are moving non-relativistically, moving slowly, you still have to put in their charge and mass. It's not predicted by what you're doing. All right. I mean, if you want an example of another pure theory, it's a pure QCD, a theory of just gluons and strong interactions. It turns out there's no inputs into that theory. But that's an example I don't expect you to be familiar with, and we will talk about it in due time. By the way, everything that I say today will be elaborated on a lot throughout the semester, and so if some of this is going, it's okay, all right, because I'm just giving you sort of a taste for what we're going to be doing. And some of it we're not actually going to do in detail, and you might be relieved at that because some of it's going to be a little awful. Okay, so any other questions about the use of these words? All right, so now I'm going to, by the way, how many of you did the pre-lecture reading? Sweet. Okay, do the pre-lecture reading. Those who did it realize it's a paragraph. It's literally something I wrote, and it's just to give you an idea, an outline of what we're going to be covering. And the reason I want you to do that is because I want your brain to engage before you walk in this room. Because then you get in the room and you're like, I have no idea what we're going to do today. Rather, you have this list and you can go, okay, this is what Forma is covering that, and this is what Forma is covering that, okay? A second question, how many of you bought a book? Okay,
Yeah.
the book is not required, all right, but it's very, very useful, okay? I'm going to give you the lecture notes, I'm going to give you these pre-lecture readings, you're going to come to lecture, we're going to have a lot of fun. I find the book a little dry, but it's really the only option at an undergraduate level. So I've in the past taught this course from that book, and students really didn't like it very much, so that's why I steered away. Okay, all right. So now what I'm going to do, that we've got some of this vocabulary down, is I'm going to go back and talk a little bit about frameworks, some mechanics, different versions of mechanics that we might use in describing physics. And we'll start with non-relativistic, or what we might call Newtonian mechanics. And I want to contrast that with relativistic mechanics. And as I do tend to let you have ample opportunity to stare at my backside, if you have a question, just ask it. You don't have to raise your hand and wait for you to call me. Okay. So now this is going to be very much in the way of a review. Just a few little details. We are going to talk about special relativity at more length in a couple of weeks, but for now I just want to kind of remind you of the distinction between doing good old classical non-relativistic physics and what you have to deal with when you encounter relativistic physics. So first of all, a couple of important points. We know, or you should know, you should at least be familiar with the idea that this is valid at low speeds. We'll quantify that in just a second. Okay. Relativistic mechanics, on the other hand, is valid when? Always. Always, exactly. It's always valid. Now, some of you might have jumped the gun and said at high speeds, but the truth is you can apply special relativity at any speed and you get the right answer. Okay? It's just if you apply special relativity to a system which is moving slowly, the answer you get will be the same one that you get using non-relativistic mechanics. That's important. Why?
Relativistic mechanics is an extension of Newtonian mechanics.
Relativistic mechanics is correct. And non-relativistic mechanics is incorrect. It's not that one is used here and one is used there. Relativistic mechanics is correct. And in this class, we're interested in fundamental physics. We want physics that is true the most number of times, in the most scenarios. So we're going to do relativistic physics. Okay? Experimentally, we have to. All right? We slam things together hella fast. All right? So when you do a typical particle physics experiment, you're often accelerating things to, you might take a proton at the LHC and accelerate it to 0.99999 C. For those of you who prefer miles per hour, that is 7 miles per hour short of the speed of light. Oh, that's a weird way to put it. Okay, so that's pretty relativistic, right? So if you tried to apply Newtonian mechanics, you would fail epically. So we have to use special relativity to accurately predict what we would see at accelerators. But more importantly, we want to do the thing that's always right. Okay, so we're going to do things relativistically. Now, just a couple of reminders for the differences you encounter, mainly because you're very, very comfortable working in non-relativistic settings, and so if we're going to do things relativistically, you should always know how to participate. So in non-relativistic settings, you are typically working in a framework where you have 3 spatial dimensions and then 1 dimension of time, which is absolute. That word absolute has a particular meaning. To really understand absolute, you can contrast that with what you work with in special relativity, which is where you work in a 3+1 dimensional space-time. And again, a lot of this will flesh out in more detail when we study special relativity a bit. But the idea here is that you're working in a 4-dimensional space. We call it 3+1 just to remind ourselves that one of them is a little bit different. But it's a 3+1 or 4-dimensional space where you can do rotations and mix time and space. Here you cannot do that. You can do rotations that mix space and space, but you do not mix time into it. So that's why I call it absolute time. All right, and then in Newtonian mechanics, we have at our disposal a type of relativity. It's actually the oldest form of relativity, and it's called Galilean relativity. And if we have Galilean relativity at our disposal, what it means is the following, and I'm going to set up a framework which is true and which I'll use in both. So if I have a frame S prime, which is moving with some speed u relative, or some velocity u relative to another frame S, and then if I have a particle in the frame S prime, which is seen moving at a speed v prime. Okay, so if you've got a person standing in this frame in S prime, so they are at rest with respect to S prime, they see this particle moving with a velocity v prime. Okay, then the question is to an observer standing at rest in S, what velocity would they see this same particle moving with? Okay. In Galilean relativity, the answer is that the velocity seen by this observer is simply the velocity of the frame plus the velocity of the particle. Okay? You know this, if you're standing on the road, the car's running down the road, the guy in the car shoots the gun. Okay, you just take the velocity of the car, add the velocity of the bullet relative to the car, and that's the velocity that you would see standing on the road. Okay, it's the oldest, most intuitive form of relativity. That changes in special relativity. What kind of relativity do we have in special relativity? With special relativity, just wanted to check. See, that would have been I would draw a card. Just to give you an idea of how intimidating that is. In special relativity, we have instead special relativity. Taught a class in particle physics at CU. They couldn't answer that. No, I'm not going to do CU jokes. I think you're smart enough to know that CU is pretty good, especially in physics, so I'm not going to. Okay, and in special relativity, we have a slightly different formula, which some of you have probably seen and working with, and that is that the speed seen by the observer in S is v, it's u plus v prime over 1 plus u times v prime over c squared. Okay, slightly different formula. But this formula is nice. As an example, there's many other formulas I could write down that are, there's a non-relativistic version and there's a relativistic version, things like kinetic energy and so forth and so on. But this is a particularly nice one because it illustrates 2 things very quickly. One, this formula, you can very quickly see that it enforces the constancy of c. That is, you can take the frame u and say if v prime is equal to c, what speed would this observer see? And if you do the calculation using that formula, you'll find out that this person sees the same speed, c. Remember, everybody agrees on the speed of light no matter what their relative state of motion. That pops right out of here, okay? If you take v prime and set it equal to c, this thing will just reduce to c. Okay? Secondly, it immediately gives us insight into what I call a correspondence principle. And correspondence principles are very important whenever we talk about taking a limited description of things and we want to try and generalize it. We want to ask, okay, well, when can I get away with the more limited description? So the correspondence principle is basically a condition. It says, if this is true, then we can just get away with replacing this expression with this expression. Well, what has to be true? Say it again?
Small speeds for U of V.
Exactly. You have to have both. If u and v prime over c squared is much less than 1, then you can do non-relativistic physics. Okay. So it's not necessarily that you say a particle has to travel with a very slow speed, but you also cannot consider changing to a reference frame moving with a very fast speed either. A lot of people, they don't see that when they talk about limiting this to non-relativistic systems. Okay. So there's your correspondence principle linking up situations where we can make do with the non-relativistic approximation to relativistic physics. Again, if you're going to do relativistic physics, which we're going to do in this class, this is never an issue because you're never going to try and make it non-relativistic. All right? Any questions about this? Is this familiar stomping ground, everybody? Good with this? All right. So this discussion is something which, for those who've taken general relativity, it's going to be relatively straightforward when we get to it, because we're going to develop special relativity in a slightly more sophisticated way than you saw it in modern physics. We're going to talk about it in terms of an SO 1,3 invariance. Okay, but for now, I just want to get across sort of these are mechanics, these are frameworks for doing physics. They're not particular physical theories, right? And this is more valid. It's valid over a greater range of velocities, right? So that's the one that we're going to work with. All right. Well, we did relativistic and non-relativistic. What do you think comes next? Say it. Say it. Quantum. Yeah, classical and quantum. Exactly. Non-relativistic Newtonian mechanics, and I have to be a little bit careful here. Non-relativistic quantum mechanics. And I'm just going to write QM. QM means quantum mechanics. If you think it means something else, you are probably not from a physics background. And that's okay. You should just adjust to this notation. All right. So if we're going to talk about moving from classical or Newtonian mechanics to quantum mechanics, at least not relativistically, then we can talk about when they're applicable. So when is Newtonian physics an applicable description compared to quantum mechanics? Anybody tell me? Large scale? Is that quite true? It used to be true, but it's not actually that true anymore.
Large number of particles.
That's what we might mean by a large scale, but even that's not true. But high energies you would definitely have to use. Well, high energies are probably, it's more appropriate for the special relativistic versus non-relativistic. So I'm going to write it down and I'm going to give you a moment to think about why this language is important. It's valid for large, I don't actually know if the word is decoherent or uncoherent. What's the word? Decoherent. It's well, I know there's decohere and decoherence. I don't know if decoherent. Decoherent systems. Why do I write that? Yes, a Bose-Einstein condensate is a large system, but it's perfectly coherent, so it behaves quantum mechanically. The reason why, when we have large systems, we typically get away with not using quantum mechanics, is that if you have a lot of particles and they each have their wave functions, it's rare that their wave functions would actually overlap and constructively interfere. Usually they just have a wash, all right? It's kind of like taking a whole bunch of random waves and throwing them together. You're not going to get some really beautiful, nice sine curve. But if you have all of your wave functions for all of your particles identical, then the entire collection is described by one big-ass wave function. And that's definitely going to behave quantum mechanically. Okay? So you're right, most large systems can be treated non-quantum mechanically, but there are exceptions, and we can cover those by saying the word decoherent.
How is this different from a system which dephases?
You mean over time?
Yeah, like, because there are lots of quantum systems which dephase very quickly, but we still use quantum to study them.
When is quantum mechanics applicable? Always. So you can use quantum mechanics to study large decoherent systems, if you prefer. Okay. Typically you don't, because it's just harder. Right? Yes.
So you mentioned as for large decoherent systems, so is that like, does a laser behave?
So a laser is something which you cannot understand non-quantum mechanically. And whether you want to call a laser a large, I mean, a useful laser, like the principle so a useful laser is achieving a rather substantial amplification in the output of the photon. So you're talking about the macroscopic number of photons emerging from the output coupler of the laser. So it's large, but they're definitely coherent. Yeah, so I guess a laser is another really good example of a system which you might call large, but it's definitely yeah, that's a good point. Other questions? Okay, so now the next point is something which is slightly different from what we encounter when we go from special relativity to Newtonian mechanics, and that is that the nature of the questions we ask and what we expect from our calculations changes. And this is really the hardest part about quantum mechanics. In a sense, special relativity as a generalization of Newtonian mechanics is much easier to wrap your head around than quantum mechanics. And the reason is in special relativity, you ask and answer the same questions. What's the particle going to do? Where's it going to be? Okay? But in quantum mechanics, you have fundamentally different questions. All right? So to review, in Newtonian mechanics, it is deterministic in the sense, and we have to be careful what we mean by the word deterministic, given initial conditions and the dynamics, and I say dynamics loosely, this could be you specify the Hamiltonian, you're going to use the Schrodinger equation, you specify the Lagrangian, you can use a path integral, there's many different ways to do quantum mechanics, but nonetheless, they all involve having something to determine the dynamics. I'm sorry, I'm classical. Why am I talking about path integral and Schrodinger equation? So I can be talking about Newton's laws of motion, I can be talking about Lagrangian mechanics, Hamiltonian mechanics, all that nice classical mechanics. But you're given the initial conditions, whatever's controlling the dynamics. Okay, this could be the Euler-Lagrange equations of motion, Newton's second law, whatever. The solution to the differential equation is the unique behavior. Okay, so you take Newton's second law and you say my particle is here moving this fast at t equals 0, and then you have Newton's second law and you know all the different forces that you plug in there. You can figure out where it's going to be at a later time and how fast it's going to be moving. Those are the kinds of questions we ask, and that's what it allows us to calculate the answers to. It indicates, it makes of us fortune tellers, predictors of the future, with the difference that we're always right. Sweet! Okay, in quantum mechanics, even if you haven't studied quantum mechanics in detail, you know that this is not the way it goes. Now, what's weird is in quantum mechanics, there is a sense of well-defined evolution. Okay, so if you're given an initial condition, then you have a differential equation that governs how that initial state evolves with time. So in solving problems in quantum mechanics, you're going through the steps very much like what you do here. But the difference is how you interpret the solution. Okay? If you solve the solution to a quantum mechanical problem, so you take, for example, the time-dependent Schrodinger equation, and I say the wave function at t equals 0 looks like this, and then you solve that the Schrodinger equation, and you find, okay, this is what it looks like at a later time, then what that tells you is not what the system is going to be doing, but rather the solutions correspond to probability distributions. writing your equation for psi as a function of x and t, and then if you take the complex conjugate squared of that, that gives you the probability for, say, locating your particle at any given position at any given time. Whereas here you might be solving for x as a function of time, and the solution tells you where the particle is going to be at a specific time. Okay. So doing quantum mechanics and classical mechanics is very, very similar. It's a differential equation with boundary conditions. It's just how you interpret the solution that determines whether you're doing classical or quantum mechanics. All right, so correspondence principles in this case are much harder to elucidate. And there are many, many different ways to argue how you get from a quantum to a classical restriction. And I'm not going to go through all of the different examples. But the reason why it's harder than it is in special relativity is because the nature of the questions change. Okay? So you can't say, I do this calculation in quantum mechanics and I get this probability distribution, and then I take some limit and I get the probability distribution I would get doing it classically, because there is no probability distribution doing it classically. Or actually what you would say is that the probability distribution goes to a delta function. It is uniquely centered on a single possibility. Okay? And that's actually the technical way that you would do it. Generally speaking, in arguing for the quantum and classical correspondence, it usually involves taking some form of action, and action is generally an unrollable Lagrangian. And so long as that action is much, much larger than h bar, then you can safely use a classical description for your system. Okay. Many of you probably haven't seen the correspondence written this way. It's a little more intuitive if you've seen a path integral construction. All right. But generally speaking, the idea here is that whether or not you need quantum mechanics is somehow controlled by how big things are compared to h bar. Now, for those of you who aren't aware, h bar has the units of angular momentum. But angular momentum is exactly what the units of action are. Okay. But I'm not just matching units. You know, hey, let's get units, let's get units, let's compare them. You know, this is actually the fundamental thing you should be comparing to h bar. All right. So you can talk about large numbers of particles in decoherent phases, and then look at the classical action and would be large compared to h bar, et cetera, et cetera. I'm not going to go into the details of that correspondence. It's notoriously subtle. But we might ask ourselves in this class, would we ever find ourselves wanting to do non-quantum mechanical analyses? We want to do fundamental physics. We want to do the stuff that's always right. So we're going to do quantum mechanics. Now, for those of you who haven't taken 320 or who maybe took it and don't feel completely comfortable with how you came out of it, or maybe took so long, you forgot it all, don't worry. We're not going to be repeating a lot of the things you did in quantum mechanics. We're going to be cherry picking a few ideas. We're largely going to be developing a slightly different, more sophisticated framework. We're going to be very limited at what we can do in that framework, but I don't want you to think coming in the door that I expect you to know the ins and outs of quantum mechanics. I do expect everyone's heard of this number, and that its size compared to something determines whether or not quantum mechanics is important. It's about the extent of which you need to know right now. Okay. So any questions before I get rid of all of these? Yes? Can I get rid of it while you ask your question? Yes.
Were you really intention like both just say quantum mechanics that it's I've heard of it, but like
Pretty good. Pretty good. Okay. So, in this course, we are going to be talking about quantum mechanical things that are moving very fast. What do you think we would need in order to describe that?
Not relativistic.
Are you one of those who is surprised to predict what I'm going to say next? Well, that's
Relatively
okay. All right. So, from my previous discussion, one would be left to conclude that what we are going to have to utilize in order to study what happens in a particle collider, because things are hella small and hella fast, or more importantly, to describe things in a way that is correct all the time, is to be doing both relativity and quantum mechanics simultaneously. Okay? And you can do this.
So earlier, when you said non-relativistic quantum mechanics was like always true, is that?
Okay, yeah, sorry. So those always, let me see. So here is where always was written. And those come with a little asterisk. That's a footnote. And the footnote down here says, and then the connection of these two frameworks. You know what I'm saying? So yeah, when I said always, it was limited to either speeds in the case of relativity or size of beats and beat coherence in the case of quantum mechanics. Clearly, non-relativistic quantum mechanics is not true if things are moving fast. Okay? And special relativity is not true if you're doing something like an atom. Maybe you're doing something more sophisticated. So yeah, take the word all with a grain of salt. What could I possibly meant by the word all? Okay, so all is actually here to a degree. This is not even all. That's the sad part. Where'd my piece of paper? You know what I just realized? There's no clock that I can see. That is awesome. That means that we've only been in here for 5 minutes. I have an hour and 10 minutes to go. That rate. Okay, no, I'm just kidding. All right. Good. So 30 minutes. So relativistic quantum mechanics is the natural sort of hybrid of putting together relativity and quantum mechanics. But okay, it has some problems. So what are the problems with relativistic quantum mechanics? Well, remember, one of the important lessons from quantum mechanics, so non-relativistic quantum mechanics, if you will, if you take a solution to the Schrodinger equation, you're say studying a hydrogen atom and you're trying to determine the motion of an electron in a hydrogen atom, or an equivalent potential with the nucleus, and you find a solution to the Schrodinger equation, what's the first thing you have to do to it before you can interpret it as a probability distribution? You have to normalize it. Okay, because remember, one of the fundamental rules of probability is that all the probabilities added up over all the possibilities has to equal 1. Right? Something's got to happen. Okay, so if you're just computing a random number, all right, then you have to divide by the total of all possibilities in order to call that thing probability. I mean, what does it mean to say the probability is 3? The probability of 1/3, you understand the 3, it needs to be normalized. So the normalization in quantum mechanics is basically achieved by saying that if we take the wave function and we integrate it over all space, so this is taking an interpretation of the wave function as where is the particle I'm studying? Well, if you integrate it over all space, you better get 1, because the particle better be somewhere. Okay? So to use quantum mechanics to calculate probabilities, we have to normalize the wave functions. Okay? We have to be able to say, I'm studying an electron, it's somewhere. And then we might be able to confine it to a box or confine it to the locality of the nucleus of a hydrogen atom or whatever, but it's got to be somewhere. Okay? But special relativity throws a wrench in that. Because special relativity introduces something which is not consistent with normalizing the probabilities. Can you tell me what special relativity is?
Length contraction.
You can actually get length contraction to be consistent. So that's a question of how large is the system, and if you do the time evolution of the wave function over some change of reference frame, and you're changing the overall volume, but still over all space, you don't length contract. Yes?
Is it the creation or annihilation?
Exactly. Special relativity introduces the creation and annihilation of particles. That's problematic because in special relativity, you can have an electron and then not have an electron. Okay? or more realistically, you can have an electron-positron and then no longer have an electron-positron because they've annihilated. So how do you normalize that? Okay. Now, there is a very inelegant way to approach this. You can take these two things and you can say, okay, so let's take relativistic quantum mechanics in sort of a naive formulation, and we can add onto it what is often called a Fock space of states. And this is a extra Hilbert space that you put in. So if you don't know the word Hilbert space, it's okay. We won't talk a lot about it in this course. But if you study quantum mechanics, you know that Hilbert spaces are a very important part of the formal structure of quantum systems to tell you what are the possible states that your system can be in. And what we have to do is, if we want to include annihilation and creation, we have to include an extra part of our Hilbert space, which allows us to change the particle number. Okay? So it's an extra piece of machinery that we have to add in if we're going to do special relativity in a quantum system. Okay? That is a way to do it, but it's very inelegant. It requires some assumptions at certain points along the way when you do calculations. But also it's not complete, and that's the more important aspect to it. Okay? It's not actually capable of describing everything. What are we after in this course? Not less than everything. Okay? We want everything. So if there's a more powerful way to do relativistic quantum physics, we want that tool. Okay? Anybody know what that's called? Particle physics? Exactly no. Exactly no. You can't do particle physics. Yeah, you have to do quantum field theory. I'm going to say quite a bit about this. Let me start with some meta comments. Number one, the standard model is a quantum field theory. It is not a theory of particles, it's a theory of fields. I'll specify the difference in a second. Number two, quantum field theory is not a theory in the sense that the word theory that I introduced. This is a framework. It's a sort of mechanics, if you will. So this is a place where we typically use the word theory, but it's used differently than the way that I would use it. But that's the name of the subject, so we'll just leave it at that. Also, this is not a course in quantum field theory. Quantum field theory is typically 2 semesters at the graduate level, and I wish I could teach you that, but A, you're not there, and B, we don't have enough time. So we're not going to learn quantum field theory here. Learning quantum field theory means defining rigorously everything and deriving everything very rigorously. We are going to take results from quantum field theory and learn how to use them, okay? So that you can just kind of jump to seeing some important results. But I'm not going to teach you quantum field theory in this course. We simply can't. But should you want to take quantum field theory later on down the road in another school or whatever, you might have some idea of where it's all going at the end of this course. Okay, so quantum field theory is one of those subjects. It's like tensors. Everybody's afraid of tensors before they actually study them. They think, quantum field theory is terrible, I can't do it. We're not going to learn quantum field theory in this course. But it is the appropriate framework for what we're going to be doing. So let me give you some ideas about why it is so useful and what it looks like. So first of all, what does quantum field theory mean? Well, if we do particle physics, that is, if we're studying a system where we assume that we have particles, then what we're after is the trajectory of the particle as it moves through space and time. Okay? So a particle, that's a particle, moves. So if I plot it in space-time, it follows a little line. It's called the world line of pure relativism. We don't need to worry about that. The motion of that can be described by the position as a function of time. That is the fundamental holy grail of describing something which is composed of particles. Where is it as a function of time? Once you know that, you can figure out its velocity, its acceleration. You can do all kind of fun stuff with it. A field is a function of space and time. A field is something that you would actually plot as a function of x and t. So you can kind of think of it as a surface. Okay? So when you do quantum field theory, instead of thinking of a little bitty point-like particle that sits here and is moving this fast, you just think of like a surface. It's actually a four-dimensional surface. Okay, and it fills space and time. And then it fluctuates up and down in field space. Okay, so I know that is of space-time. So it's kind of like if you took water, it's like fills spatial volume, and you look at density fluctuations. They're not actually fluctuating in x, y, and z. They're fluctuating in density space. It's kind of like that. We'll make an analogy. Now that's what field theory looks like in general. But you can ask, what about a correspondence principle? After all, we know that in many, many situations things look a lot like particles. Well, if I take a field and I look at a solution where the configuration of the field is completely smooth and flat except for some very small localized excitations in field space, then this configuration will look like particles. Okay? This context and this going from a continuous system to particle-like things happens in many different branches of physics. You can talk about photons and vibrations in the condensed matter systems. You can talk about, of course, photons and electromagnetic systems, but there's lots of places where you can find this kind of particle level.
Real question. So, for like the concept like value of the field, does the contours like have that value, like have any significance?
The contours,
Like, I guess I would say, if you were like to take a plane at a one value of the field, like just like say like for the field equals 5, like arbitrary, like there's like the contour lines. I don't know, because like I'm seeing this as like a sort of like to create a surface. Is that like?
I use the word surface to give you a visual. It's not a surface. It's not embedded in anything. It's actually a space-time filling. That's why I thought the pressure of water is maybe a better way to think about it. Okay, keep stewing on your question, and we'll talk a little bit about the class. Does anybody else have any issue with this picture? I mean, I'm giving you sort of a way to wrap your head around it, but it's considerably more complicated than that. Yeah.
So like a localized excitation of a gravitational field would be a massive particle?
No. A localized excitation of the gravitational field would be a graviton.
Okay.
So particles are not gravitational fields. They are matter. I'll talk about what that means in a few minutes. Okay. But yeah, look, these are concepts which we're going to revisit again and again and again. So I don't completely expect you to digest it in this first introductory lecture. And indeed, I don't even know if you're going to emerge from this course with a really firm appreciation of this, because quantum field theory it just takes that much to wrap your head around it. We're going to try and go beyond that to some more interesting things, but I'll be happy to entertain more about this.
Does quantum field theory discuss GR, or I thought it was kind of
No. I'll talk about that in the semester. There's places where I'll make connections, but GR is a field theory, and you can quantize it. And when you do, you have problems, and we'll talk about that in the course of the semester. So, but for now, let me go ahead and explain to you. I said previously that relativistic quantum mechanics is not complete. Let me explain to you what field theory does for us. So there's quite a few things that quantum field theory provides that makes it far more preferable. It gives a natural origin to identical particles. That's one of those things which you just kind of have to take with a grain of salt when you're studying quantum mechanics the first time around. You say two electrons, no matter where they are in the universe, are absolutely identical. Well, how the hell will they know to be identical? Okay? How do all electrons know that they have to be exactly like every other electron? Well, in quantum field theory, it's natural because they are just two different excitations of a single field, the electron field. So it's like you got the water, you got the ocean, you got a wave here and a wave here. How do they both know that they're water waves? They're the same body of water. A little ripple over here and a little ripple over there. So there's a very natural origin to this identical particle, or identicality of particles that we encounter in nature. A technical thing, which I'll be able to explain more when we actually get into some calculations, but it gives natural weights to creation annihilation processes in finite diagrams. This was something which you had to put in by hand if you were just doing relativistic quantum mechanics, and it falls out naturally in quantum field theory, but that's a technical thing I'll talk about later. It's only in the context of quantum field theory that you can derive the spin statistics theorem. Does anybody know what the spin statistics theorem is?
Symmetric and asymmetric function.
It involves that. Does anybody know what the spin statistics theorem is?
Half of interspin particles have to obey any symmetry where the symmetry is asymmetry.
Yes, so the manifestation of this, which you were first introduced to, was what was called the Pauli exclusion principle. It says if you have two spin-and-a-half particles, they can't exist in the exact same state. If you study quantum mechanics at the level of 320, what you'll learn is the reason that happens is because if you have spin-and-a-half particles, their total wave function has to be anti-symmetric under the exchange of the particles, and that means that if you put them in the same state, that would automatically be symmetric, so it's not allowed. Bosons, on the other hand, integer spin particles can exist in the same state, so they obey what are called Bose statistics. All right, we'll talk a little bit about statistics later on, but that's just a result you will see in quantum mechanics, and you can only prove it from quantum field theory. Okay. Again, you just take it as with a grain of salt when you study quantum mechanics. And the last, and perhaps most significant advantage of quantum field theory over relativistic quantum mechanics is that it allows or accommodates what we call non-perturbative phenomena. Okay. A heuristic way of thinking about that is particles doing things is perturbative. Particles are small, okay? Non-perturbative things are big. You can't describe them with just particles, little fluctuations. So examples of non-perturbative phenomenon that are part of the standard model, which are important and you can only use quantum field theory to describe, are things like spontaneous symmetry breaking and Higgs mechanism. Okay. So if you did use quantum field theory, you could never explain where mass comes from. Okay. So this is something which we'll study in more detail. Okay. So in the bit of time that we have left, I have a slide here which I might or might not delete from the notes afterwards, but there is many different ways that you can do classical physics and quantum physics and relativistic physics and non-relativistic physics. You've all seen Newton's laws, I know that. Many of you have seen, okay, how many of you have seen Newton's laws? How many of you have seen Lagrangian mechanics? How many of you have seen Hamiltonian mechanics? How many of you have seen three-eared giraffe? Okay, so you might wonder, like, okay, when we actually start doing things, what are we going to use? Well, it turns out that if you want to sort of most nicely understand all of these different limits using one framework, Lagrangian mechanics is the best way to go. Okay, and I'm not going to detail how you formulate, each of these different contexts using Lagrangian mechanics, but we are generally going to be working with Lagrangian mechanics. We will have a lecture a little later on where I remind you of the basics of Lagrangian mechanics, because we're going to take that and then we're going to generalize it to the Lagrangian mechanics of relativistic field theories. Okay, so if you don't remember what you learned in intermediate, or if you haven't taken intermediate, it's okay. We'll have a little break where we talk about that. But again, I'm going to skip that discussion for right now because what I want to do is get to a quick overview of the standard model. So What I'm about to put on the board is going to be, if you haven't really studied it, is going to be dizzying. And then I'm going to show you something on the overhead which is even worse. And then I'm going to let you leave and worry. Okay, so the standard model. Hitherto referred to as SM. Not S&M? SM. Okay, there's a difference. We don't say standard in model. It's standard model. Okay. By the way, when you write, you capitalize standard model. You do not capitalize any other physical theory, but for some reason standard model isn't accepted. So we write capital S, capital T. We don't write capital G, capital R. For special. Okay, so why? Because it is the right thing to do. Okay, so what I'm going to do is I'm going to give you a layout of the content of the standard model with some ideas about why it looks the way it does, and these are all details which we're going to develop much more fully throughout the semester. Okay, but to begin, the standard model is a theory of fundamental fields, but we're often going to refer to the particle-like behavior of those fields. So I will refer to particles, but when I'm referring to a particle, what I mean is a localized excitation of a field. Okay? But these are fundamental. What do I mean by that? What I mean is, if it's made of something else, it ain't fundamental. Protons, not fundamental. Neutrons, not fundamental. Okay? What I want to lay out right now is that part of the standard model which is not made of anything else. Okay? Because once you start going into composite things, the sky's the limit. Okay? Yes?
So does that entail that a proton, for example, is a triple excitation of the quark field or something like that?
A proton is a bound state of 3 quarks.
And so in this framework, we would describe that as from the quark field.
Yes, exactly,
Okay.
exactly. All right, so what are the fundamental particles or fields in the standard model? Well, we can break them up into 3 categories, and those 3 categories are based on the role in the standard model of what those fields do. So first of all, we have the force fields. And generically, these go under the name of mediator particles, or they're often referred to, for reasons we'll learn later, gauge bosons. Sometimes they're called messenger particles. Okay? And we have 3 different varieties of these. For each force in the standard model, we have mediators. For electricity and magnetism, E and M, we have the photon, gamma. For the weak interactions, we actually have 3 of them. We have what's called the W plus and minus bosons. That's a W plus and a W minus. I'm just going to be compact in my notation, but you always either have W plus or W minus. And then what's called the Z naught boson. So 3 of those. And then for the strong interaction, it gets more complicated, and it turns out that we have 8 gluons, and I'm not even going to write down the separate gluons. Okay, there's 8 of them. All right. Yeah.
So there's a force missing.
Okay. Yeah. So the standard model. So the standard model, as a relativistic quantum field theory, is a description of the interactions of things, assuming the absence of gravity, which is accurate for any experiment we do. Because if you're doing a high energy particle experiment, the effect of gravity over the effect of all of the other forces is ignorable. Okay, the time frames are very short, the masses are very small, the gravitational effects are negligible. Okay, and you can actually calculate the magnitude of what the gravitational effects would be, even compared to electromagnetism. So we could add in gravity, okay, but then we have to ask, how do we do that? We could just stamp general relativity on top of it, but that's classical, and that's not going to be particularly nice. We can quantize gravity, but that has problems which we'll encounter in the semester. So the standard model is only going to be the three interactions, the electromagnetic, the weak, and the strong. Okay. And we'll touch on gravity when we can, but it is not generally a part of the standard model. This word is important. Bosons. Yeah, that means they have integer spin. In fact, all of these particles are spin 1 particles. Okay, so all of the force particles are spin 1. The second category of particles you might call stuff. It's what you're made of. Okay, but a better name for it is matter. All right, it's the things which we're actually made of. Not forces between them, but the actual things, the building blocks. And it turns out that matter is described exclusively by fermions. All fundamental matter particles are spin 1/2. Okay, unless you go to supersymmetric extensions and things, and then you get to spin 3/2, but for our purposes, spin 1/2 is enough. Okay. Now, the matter of the standard model can be conveniently broken down into 2 categories. And again, all of you say, he's drawing more arrows, make them stop. But these arrows are important because as we develop the standard model throughout the semester, you'll go, oh, okay, I understand why Florida was drawn on better than arrows. These can be broken, all the matter can be broken down into what we call 2 families. And the first family is what we call the leptons. And the second family is what we call quarks. Okay. Now the good thing is that we're almost done because these only break down into 3 subcategories. And I promise you this is as far as I will go. So we have 3 generations . Okay, we have 3 generations of leptons, and each generation is actually composed of 2 leptons, confusingly enough. There's the electron neutrino and the electron. There's the muon neutrino and the muon. And there's the tau neutrino and the tauon. Okay. And similarly, the quarks break down into 3 generations of 2 quarks. So we have the up and the down quark, we have the strange and the trim quark, and we have the, confusingly enough, bottom and top quark. I know. Where these are written this way in order of ascending mass. That's why these 2 are actually switched. The top quark has a larger mass than the bottom, so it gets to be on the bottom.
What's the middle word?
Strange term. Okay. Now, so if I asked you how many particles of matter are there in the standard model, you would say? A lot. You would say 12 times 2, because every particle has an antiparticle. Okay. It turns out if I come up here, I can almost say the same thing, except this is its own antiparticle. This is its own antiparticle. These are each other's antiparticles. And then several of these are antiparticles to the others.
Are any of them their own antiparticles?
Say again?
Are any of the strong blue ones their own antiparticles, or are they all pairs?
Some of them are their own antiparticles. Some of them, but not all.
Do any of them have any particles that aren't already included in the zinc?
No.
Okay.
No.
So that's also.
It's also. Okay, so we're missing something. What are we missing? Say it again? The Higgs, exactly. So here we have force particles, we have stuff, and then we have God. Particle physicists don't actually use that word to describe the Higgs, but I don't know, it made its way into the popular literature, so they do it. And the Higgs is actually a spin 0. It's a boson, hence the Higgs boson. So force particles are bosons, the Higgs is a boson, this is spin 0, these are all spin 1, and then everything that you're made of is spin 1/2. Okay? Now, that's important to note because it means if we want to do calculations and describe this stuff, we need to know how to calculate things where the spin is 0, where the spin is a half, and where you have spin 1. Okay, we can't just do simple old spin 0 for everything. It's not going to fly with the same model. Now, you might say, why do you organize it this way? Well, I organize it this way for a couple of reasons. One, this organization is clear. These categories play very different roles. This is stuff, this is the forces between stuff, and then this is that special thing which gives rise to mass. We'll talk more about that later, okay? But why do I split it here? Can anybody tell me? Well, this splitting hopefully is obvious. There's 3 forces. So why do I split it here?
Leptons are, like, we think of them as themselves. We work with electrons, whereas quarks we bundle together to make something.
Well, that's close, and it's related to the answer to this question. Peter?
Strong versus weak interactions?
No, it's just the strong.
Just the strong.
Okay? Only quarks feel strong interactions. These do not. Okay? So if you're talking about a strong interaction, you can ignore all this. You can just focus on quarks. Okay? However, they all feel the weak interactions. The weak interaction is the whore of the standard model. It gets everything. Okay? Everything feels it. But the weak interactions are the reason why I put these in pairs. Because it turns out that the weak interaction actually acts to rotate this like a little 2-component vector, and rotate this like a 2-component vector, and this, and this, and this. And we'll see that in detail. So the reason these things are in these little doublets is because of the weak interaction. Last but not least, what about electricity and magnetism? What does that affect? Anything that has electric charge, and that turns out to be this, this, and all of these, and this. I know. Okay. So these sort of splittings and groupings and so forth are because of the structures that we see in the standard model. Again, these are details which we'll see throughout the course of the semester, but I just want to kind of give you a blueprint to be filled in due time. So, and again, this will appear in the notes, so you don't have to worry about that. Now, coming back to what David said. You guys can't sit next to each other, you're confusing me. About binding things together.
Yeah, just remember by that.
So one thing I'll say is, has anybody got to run out in the next 5 minutes, or can I get through? Okay, good. So 5 minutes tops, I promise. So another piece of language in the framework of the standard model that we're going to encounter time and time again is dealing with the quarks, because it turns out, for reasons we will learn, that quarks never exist by themselves. They always exist in bound states. And we will uncover why in due time, okay? But because they only exist in bound states, it turns out that if you take all the quark bound states, you can actually divide those into 2 categories. So we have, on the one hand, what are called, so generally bound states of quarks are called hadrons. Okay, so if you run into the word hadron, it just means some bound state of quarks. And generally when we do high energy physics, if we're not dealing with one of these leptons, we're dealing with a hadron. We're never dealing just with an up quark, because up quarks don't exist by themselves. Okay. So if we take all the hadrons, we break them up into 2 categories. There's the mesons, which are 2 quark bound states, and the baryons, which are 3 quark bound states. And we will understand why 2 and 3 quark bound states are the cases we encounter later on. Okay. So for example, the proton is a baryon. Okay, it's a bound state of 3 quarks. Whereas the pi meson is, no surprise, a meson. It's a bound state of 2 quarks. Okay, we don't find bound states of 4 quarks, bound states of 6 quarks. Could, but they don't exist for any appreciable amount of time that we can read them. Yes?
Can you make both of those with any quarks, or are there like specific pairs?
Yeah. We'll get into the structure of all this with anti-quarks in due time. Yeah, but anything I do with quarks, I can do with anti-quarks. I can mix quarks and anti-quarks, strangely enough. Yeah. So there's lots of those things. Yes.
Are baryons intrinsically more stable than mesons?
Like, what
No, I can't make a blanket statement about stability. Yeah, stability is something you have to calculate one particle at a time. Go ahead, John.
Falling back a little bit, is there an antiparticle to the Higgs?
At present, I think the Higgs is its own antiparticle, but the data's still out on exactly what the structure of the Higgs is. There might be more than one Higgs. That's kind of a frontier of the standard model, which is pretty established. So I promised you that we were going to be doing Lagrangian mechanics. So we should probably have a look at the standard model Lagrangian. That's it. And you might be relieved to know that at no point are we ever actually going to write this thing down and use it. But I show this to you because if this was particle physics, I would have never gotten into particle physics. Okay, this is just terrible. It's awful. But what's beautiful to me about particle physics and why I get excited about teaching this course is that for as complicated as that looks, the reason it looks the way it does, you can trace back to the presence of symmetry. So a very pervasive theme in this course is going to be symmetry, because symmetry governs why the standard model looks the way it does, why these things break up the way they do. Okay. So to that end, I'm going to finish today's lecture with just a quick outline of what we're going to be doing this semester, just so that you have an idea of when we're going to hit certain things and what we are going to hit and what we're going to skip. So very quickly, in course outline, it would look something like this. We're going to start with a systematic approach to transformations and, more importantly, symmetries. And we're going to develop the necessary tools of group theory and group representations to have a precise mathematical way of treating transformations and symmetries. That's going to be important for understanding the structure of the interactions, the weak, strong, and electromagnetic, but it will also prep us for a more sophisticated way of understanding special relativity, which we will review. Okay, briefly. So I will review special relativity, of course. We're also, again, going to review Lagrangian mechanics. All right? And then we're going to extend Lagrangian mechanics to relativistic fields of spins 0, 1/2, and 1. Okay, when we extend it to spin 1/2 particles, we're going to encounter the famous Dirac equation and the prediction of the existence of antimatter. So all of that is going to come along as part of the discussion there. And then, now that we've got sort of particles and how to describe them, we're going to introduce interactions through the principle of local gauge invariance. And we will see how symmetries in the standard model are actually the source of the interactions. That's one of the most, I think, beautiful parts of particle physics is this description right here. And then after that, we'll be in a good place to talk about spontaneous symmetry breaking and the Higgs mechanism. So we will talk about the Higgs mechanism, why we use it, how it's actually used. And then if we have some time, we're going to devote a few lectures to special topics. That's the first half of the course. That is what I would call formalism. So for those of you who took GR, it's a lot like the first half of GR, where we just develop the formalism of the theory. The second half of the course is calculations. Okay, we've got all this formalism, now let's actually calculate something. Let's calculate what you go and measure, okay? And that actually sounds a little bit boring until you get to the very end, and then it gets really interesting. So we'll start out by laying out calculations in the sense of what would we want to calculate. It turns out lifetimes of decay rates, lifetimes and scattering cross sections are the key things we want to calculate. We'll talk about why. We'll review, or for many of you introduce, perturbation theory. Okay, it's something, if you haven't seen it, it's the backbone of how you do calculations in this subject. So I'll review what that means and how you might have seen it in the past. And then we will extend to perturbation theory as it's realized in the Feynman calculus. So you will learn how to construct and calculate with Feynman diagrams. That's, of course, a very important part of particle physics. And it is actually a way of doing perturbation theory. We'll very quickly review some classical calculations. And here, classical doesn't mean classical, it means classical. You know, some classic lifetime calculations that have been verified in experiment. Just some of those things, you know, peck around the chest kind of deal. Or hopefully not peck around the chest, if you won't around the chest. Okay, and then the last one is where it gets interesting. Once we know how to do calculations, it's going to let us calculate a very, very interesting effect, which is going to force us into a topic this is generally called normalization. And I say this because this is perhaps the most intriguing part of what we're going to do this entire semester. Because it is only when you start studying renormalization that you begin to realize the standard model is not complete. There's got to be something deeper. Okay? Now this story in and of itself is going to be really, really interesting. Okay? But more interesting perhaps is that it's pointing to something underneath it. And if we have some time, I will give you some hints about what might be underneath it. But that's all based on where we get to. Yes?
So if there's evidence to say there's something deeper, are we really studying the fundamentals then?
Exactly. You've got to at a certain point figuring out if what you're doing is complete. And then if you find it's in it that either you're not explaining the experiment or that it is not consistent with itself, that's what we're going to find with normalization, then you need something deeper. Of course, from the outset, we can already say, if you're not putting gravity in, it's not complete. Okay? But it's actually in the context of renormalization that we understand why gravity is a problem. All right, thank you for your attention. If you need to talk to me about anything,
Really,
cool. We're trying to see
So the first challenge, remember how to get out of the building.
That is kind of a challenge.
Where are you going? You go that way. I don't know. Take 1, 2, 3. Oh no, just like Did you even press record?
Yeah, it's been recording for an hour and 25 minutes.